Andrew Ng, an expert in AI, talked about this as well. He mentioned that we can use large language model or LLM as a reasoning engine for your business. In this table, what I'm showing you is the capability of the Gemini large language model in comparison to the GPT-4 models from OpenAI. I don't want to actually compare them, but I want you to go see that these models have been evaluated for their reasoning capabilities. In this table, there are three types of data sets to test the LLM's reasoning capability. You don't need to know what they are, but essentially the LLM models that will be created in the future. And it will be used for something like a chat GPT or Gemini kind of slash Bard needs to be tested for reasoning capability because people will now use it. The general public will probably use it more and more. I will give you an example here of the data set called Hello Swag. To summarize, this is a data set to test for common sense reasoning in everyday tasks that the models we need to be evaluated on. So what is it? What is the Hello Swag data set? It stands for harder endings, longer context, and low shot activities for situation with adversarial generations. It has no meanings for commoners like me, but it's a data set. I'll try to explain it. It's a data set that kind of challenge the model to pick the right answer by adding adverse answers for the model, try to fool the model to pick the wrong answer. This is what they mean by adversarial generations here. Um, and also longer context, harder ending is like it's so ambiguous that all of these can happen. All of these answers can actually happen. It doesn't mean that it would not happen at all. For some really, really odd chance, the answer A can happen, but most likely not. Longer context means uh, the, the sequence of words are longer. Therefore, it's more challenging for the model to understand and probably leads to difficulty choosing the right answer. So this is kind of data set. How it works is uh, the model, the LLM, will be given a situation. For example, the situation is a woman is outside with a bucket and a dog. Dog is running around trying to avoid a bath. Well, human will know that the woman is trying to give the dog a bath, and she needs to she needs to do something so that the dog will be bathed, right? So the right answer is C. She needs to get the dog wet, but the dog is trying to escape, right? So it runs away. This is the most likely answer. If human reads it, human would pick this answer, but the rest is just very unlikely. So this is very difficult for models probably like 1 or 2 years ago. Uh, but for now, the GPT and the uh, Gemini models are kind of getting better at that, getting better. Like 95% is probably considered this as a solved problem uh, at the moment. Um, but you can see here that this is some kind of the challenge that the LLM needs to go through in order to exhibit reasoning engine. Now, before I show you the actual use case, I want to give some background about reasoning skills. This is from me reading off the internet and trying to summarize what I've learned. I thought there are three types of reasoning. The first one is induction. Induction is like you have observed something, you have some samples, and you are trying to make generalization statement as a conclusion. This is induction, right? So it's going from small set, and then you create rules to covers the larger set. For example, You observe that the sun has risen every day or in your life on the east. You probably conclude that the next day and the days, so many days after that, the sun will rise every day in the east. But this is generalization. There's no backup that the sun will still rise tomorrow. It could happen that it suddenly blows up and, you know, there is no sunrise anymore. So this is induction. Small set to a bigger application or generalization. The second one is called deduction. Deduction is when you're trying to make a conclusion based on a premise. You have a premise, or you are given a premise that this is true. What can you derive? You derive conclusions based on your premise. For example, the premise one, humans are mortal. Premise two, you're given that Socrates is mortal. Oh, sorry, Socrates is human. So with these two premises, you conclude that Socrates is mortal. That's it. The situation is that you are given a premise, a bigger picture, or a ruler, and then you need to go conclude that with that logic. The third one, abduction. Abduction is, according to this, is that it's when you are finding a conclusion that is based on a logical derivation by the best explanation that you can do with your limited information or limited knowledge. An example that probably give you a clearer illustration is that your car won't start in the morning. So based on your knowledge of the car and maybe previous experience with your car, or maybe your friend's experience with not working car, you can hypothesize, you can conclude, or maybe uh, assume that the battery is dead. Now you identify the plausible reason for the car not working. So this is abduction, best explanation within the limited knowledge and information. Um, to my knowledge, induction is more like creativity. LLM is pretty good at that too, but I'm probably not going to use LLM for induction. I don't want it to say something like, okay, uh, the sun will rise tomorrow, for example. I don't think this is what I'm going to use it for. But what I'm going to use the LLM for is deduction and abduction. Deduction, again, is you have a premise and you are deriving the conclusion from the given premise. This is math and physics. All the science, we have premise or theory or theorem, whatever it is, it's a premise, and then you derive everything there. So if you want the LLM to do math, deduction capability, uh, you can use it. Abduction is useful as well. Given the situation of the car not working, you can ask the LLM, what can happen to my car? It doesn't work. The LLM has limited information, it has limited knowledge based on the training set that it has. So it should be able to do some abductive reasoning for you. So this is a type of the reasoning. And well, I went ahead to explain this. So in real life, the reasoning tasks that I think I will probably use a lot, and you will probably use a lot as well, is math. Um, in your business, you probably have a lot of math, right? A lot of math. Profit is income minus expense. It could be something else, well, maybe like risk analysis, cash flow projection, or even like conversion rate or click-through rate. If you are doing some e-commerce or website, uh, they are mathematical calculation, and you can use LLM to help it with you. Programming, for those of you who have dealt a lot with automation or writing code, or computer simulation, even plotting charts like sales charts, bar charts, whatever it is. Um, I think this is deductive reasoning as well, and the LLM is actually pretty good at this. Very pretty good at this. Um, the last tools are actually examples of abductive reasoning, like identifying cause to my problem, like car didn't start, what can go wrong. I'm writing my blog post, I can ask it, okay, what is wrong with my article? Maybe grammar, maybe punctuation is missing. Help me find it, finding the cause. That is not something not working. Or troubleshooting, right? You can ask it for, okay, help me correct my Excel formula. I want to do blah, blah, blah. Tell me how to do it. I didn't get it right. Or um, my click through rate is not so good with my product offering on my e-commerce website. What can I do? How can I fix it? So this is a type of reasoning task that the LLM can actually help you do stuff. Well, now is an example that I want to show you that the LLM can help as well. Um, let's assume that I want to kind of like engage my customers who is probably going to be a general public. What I want to do is I will go to a festival. I set up a booth, and I will hold a lottery game. The player, general public, I mean, can uh, pay to play, maybe like $1 to spin this lottery wheel. So I want to know, if I do this, am I going to make money? And what's the chance of me losing money if I am doing this spinning wheel thing? So there are factors I can think about. Okay, if I create a spinning wheels, how many wedges do I need to make in the wheel? What are my price mechanics, like how many tiers, and for each tier how many wedges they get? The top price should have one for sure. And what's the price, like monetary value for that, for each price? How should it be? And if I want to, well, probably need to pay the festival for having a booth there, uh, and so on. How am I making sure that I can make money? This is math. You can go with your gut feeling for sure. Like, there are ways to do it. You can go with your gut feeling. You think you have done this before. You have heard that people have done this before and it works. It doesn't lose money. Lose money. Go for it. Or you can use math skills of people, which probably not that easy to find. To be honest. The last thing is, now you have the LLM math to help you. So I'm going to skip the gut feeling part for sure. I will do two things: the people math and the LLM math. For the people math, relies on my expertise of math on statistics and probability, and we will compare with how the LLM is doing. All right, let's get started. But before I go, this is a thing that we need to set up. We need to set up rules for the gameplay, right? This is some kind of parameters that I decided for now to start with. Players spend $1 to spin the wheel, and there's only one gold prize, which the player who wins will get. This gold prize will get $10. There are two silver prizes, each is $4, and four copper prizes, each with $1. So this is my initial setup. Okay, let's go and take a look of how this is doing. I decided to use Google products for this. So again, I have put in some parameters. A price to pay is $1. We are getting $1 because people are paying us to play. And this is an assumption. All the wedges in the wheel, there are 30 of them. But using Google Sheet, I can change it to whatever I want. But let's start with 30. And according to my setup, gold price is 1. Uh, uh, silver has 2 wedges. Copper has, 4 wedges and $1. And the rest is probably, you can calculate it. It's 30 minus 1, 4, 1, 3, and 7. So 23 with no prices. This one use a formula to calculate that, so it will update when I change things. Okay, now these are price associated with the monetary value associated with these price tiers using probability. So if a person spin, there is a chance that it will, or he or she will get the gold price. The chance is calculated by 1 divided by 30. For silver is 2 divided by 30, and so on. So I use a formula here. You can see that it's this divided by that. I'm not going to explain the theory of probability, but this is how it's doing. The probability of landing for each tier is calculated like that. So now, before I going to calculate the expected value, the technical term again, of people winning or how much it costs, I need to calculate the actual cost. The actual cost, why is this, is that people have to pay me $1. If they win 10, I'm losing 10 minus 1. So I'm losing $9. So it's my cost if people actually get this price, right? For silver, it's 4 minus 3. So 4 minus 1, so it's 3, and so on. So this is a cost that will be realized by me if actually the people actually win the prize. Now, according to statistics, the expectation value actually means if you are doing the experiment for a very long time, and in this case, if you have like millions or 10 millions people playing, this is the cost that you are paying for the people to pay. This is the cost that I spend for people playing, right? If people are going to play and then win gold, I need to spend 30 cents for him for per person. For silver is 20 cents per person. For copper, I don't care. I don't lose anything. But for a bummer, so people who don't actually win anything, I'm gaining 77 cents per play. So the actual formula is this: the actual cost multiplied by landing, um, and then I sum up everything here. Why do I sum it up? Because in any case, there are 4 possibilities, right? People get gold, people get a player gets gold, player gets silver, player gets copper, and the last one, players get nothing. They are independent, and I have to sum this up. So when I sum it up, it gives me minus 0.27. Again, minus mean I gain. So technically, per person, I am about to gain 27 cents per player. This means that I'm winning in the long term. I'm winning in the long term because I'm gaining about 0.27 per person. But it doesn't mean that I get this every when it comes, right? For the let's imagine that person's 1 comes in and play. He gets 10 gold price. I'm losing already. I need to pay him 10, but I get $1 back. It means I'm losing $9. And if for some reason I cannot hold my game anymore, I stopped it. Oh God, I lost $9. But I can, if I keep going, 10 people, 30 people, 100, 1,000, a million, I will tend to make money. This is what the value is. Okay, but that's not the end. You don't know if you are actually going to make money just yet. As I just mentioned, if it happens that there is only 1 player, you can lose. You can lose money again, right? Now, it's getting difficult. If I want to say that, okay, I am uh, setting up a booth for 1 day, and I expect to have about 100 players or 100 customers. With 100 customers, can I make money? You can do it in Excel, but it's crazy difficult. This is difficult because the winning structure, the award structure is very uh, it's not easy to do. So we'll get into this question later, but let's see if the LLM can do this part. Can it gives me the expectation value of the uh, expectation of value of cost that I expect to pay or to gain? First, I need a prompt, right? Uh, I have already made a prompt to get it handy. So this is my prompt to the large language model. I explained the game to the model. Here's a game. A player pays $1 to play the game, which is a spinning lottery wheel. A wheel has a total of 30 equal wedges. The following is a table that explains wedges for their counts and price. Wedge type, the columns of the table, there are wedge type, counts, and price. For gold type or gold tier, there's only one, and the price is $10. $10. So silver has two prices, and each is $4. For copper, there are four price, four prices. Each one is $1, and the others is the rest. I want to know if the LM can fill in the gap too. I don't want to calculate it myself. If I'm a human, I know that right away it's 30 minus 1 minus 2 minus 4 is 23 that we saw there. I want to know if the LM can do this part or not. Now, I give it a condition, helping it. Using knowledge in statistics and probability, what is the expected value of the cost that we incur to the game owner, me, per player? And I ended up with, let's think step by step. This is a technique called chain of thought. It actually nudged the LLM to think out loud to get to the answer, and it actually helps to get to the right answer. All right, let's go with Gemini here. Gemini.google.com. Uh, Start a new chat. I put in my prompt right there. Let me just increase the size. Okay, moment of truth. It's less than 4 seconds. I'm pretty happy with the result. The speed I meant. All right, what it's saying. Sure, let's calculate the expected cost of the game owner incurs per player. The expected value of an event. Okay, it's explaining blah blah blah. The reasoning from the study of statistics and probability. But now it's doing the steps. Define the cost for each outcome. Okay, it knows the cost. Well, I put it in the table. At least it understands the table correctly. Calculate the probability of each outcome. It's actually pretty good. Look at that. Gold, the probability of having gold price out is 1 over 30. So it's 1 over 30 probability. 1 over 30 is here 3.33%. Does it match to my Excel sheet? Right on. 3.33 and so on. 2 is okay, that's good. 2 and copper. And look at that, others, 23 wedges. It knows how to calculate that value, right? Pretty good. Now, the third step, consider the expected cost for each outcome. Okay, saying that we multiply $10 uh, with the probability, we have this value, and kind of say that, do the rest for all outcomes, and then we sum it up. bad. Let's continue. We'll sum it up for expected value. Okay, it's doing that. 10 multiplied by 1 over 30. Here comes for the silver price, the copper, and the other price. There you go. This is the cost. Therefore, the expected cost you incur per player is this. Oh, do you think it's correct? It's missing something, you know? It's actually missing the um this one. It's missing that I'm gaining $1 per play. So if we actually forget about that, can we? Actually not right, right? There's something wrong there. I'm not quite believing this yet. Okay, let's compete. I'm going to ChatGPT 4. Right here, ChatGPT 4, giving it the same prompt and see how it's doing. Wow, it kind of answered right away. Like really right away. Okay, probability for uh, gold 130, 230 for silver, copper is 430. Actually doing pretty good. It's analyzing. Okay, this is a pretty cool feature of the GPT-4. It's actually using agents. It's actually calculating um, the actual values from calculator rather than from the LLM itself. Look, so the expected payout per spin is 73 cents. But event because we gain $1, therefore we have to subtract from $1. So the expected cost that will incur to the game owner per player is approximately 27 cents. This is actually what we found. Look, I don't know what's happening with Gemini. Maybe it doesn't understand us properly. This is like way wrong. So sorry, Gemini, you lost again. ChatGPT correctly calculate the value of this problem. Now, I'm going to ask it a more difficult question. I want to ask, if we have 100 players, what's the chance of not losing money if we are actually need to pay rent for the booth as well for $50? Let's do this. So it's explaining that. Okay, while it's analyzing stuff, this is difficult problem because we can't really apply statistical models right away. If we only have one price, let's say gold price, and the rest is no price at all, we can apply what we call a binomial distribution to this situation, and there are closed form formulas that allows you to count to do this. But since we have three award tiers, we need to do simulation. What I mean is that we create, um, well, artificially create 10 players and we roll the dice if this player is winning or not. Each one, each of them. And some of them will win gold, some of them will win silver. We don't know. And we actually calculate the money we lose and we gain from that set of 100 players. And we actually do this set of 100 players so many times, and then we will eventually see the distribution of the money that we get and the money we lose. And this is what they are doing, right? So it's saying that we need to do some calculation. Expected earnings, blah blah blah. Total, okay. Actually, this wow, this is not the answer that I expected. Actually do what we call Okay. Okay, this is unexpected. Um, Admittedly, I tried this yesterday and it actually made the Monte Carlo simulation, which is the situation that I just described to you. Here, it simulate 100 spinning wheels and then calculate the total payout and then see the distribution of this total payout. Uh, and then it says that this is doing right based on the Monte Carlo simulation for 1,000 sets, and including that we are needing to pay rent to the festival owners, I guess, festival organizer. We have a chance of about 12% that we are actually losing money, meaning that we don't make money enough from the game to pay the rent. And this is the code that chat GPT helps create Python code that you can actually run this, you can actually modify this to a different reward structure. Here you can change number. Okay, if you know that, okay, this your festival day, you will have probably 10,000 people coming and you can attract at least 1,000 people. You can change this number. You can copy this code and go to your Python like editor like Jupyter Notebook and whatever. You can edit this code and you calculate the probability. So yeah, I think this is really helpful. I'm not sure how this answer came about, but I'm not trusting it. I know by my gut that this calculation is not that not that easy to just use the expected value just yet. But I'm glad it happened. So I can tell you that there's such a thing called Monte Carlo simulation. If you're not sure about the LLM capability, ask it to do Monte Carlo simulation for your probabilistic problem. All right, you're lucky today. The problem happened. Okay, um, back to what we were before. Before I jump into this example here, what we were is that the LLM has reasoning abilities that can help you do your business in real life, especially math, programming, identifying causes, and troubleshooting. You can ask it to do difficult situation that, as an example, is this probability game. Thank you very much for watching our video. If you like it, leave a comment. And don't forget to subscribe to our channel, Case Done by AI, and see you at our next video.